Hello and welcome to Calculus 2. My name is Ira Rosenthal and I will be the instructor for the series of recordings of different topics taken from Calc 2. The first thing I would like to do with you today is to take a look at the topics that we will be covering in this course. We will be beginning with the techniques of integration, and we're going to continue on with applications of integration. And then we'll move on to infinite series, and then the last topic will be just miscellaneous topics a little bit put together. And let me just tell you that in our textbook, as a matter of fact, the applications of integration comes first. But we are covering techniques of integration as our first topic. The reason for that is because I find that students, after Calculus 1, they still need quite a bit of practice in their integration techniques. And the moment we start with applications of integration, your techniques need to be very, you need to be very proficient with your techniques, and there's no time to practice it. And I find that students don't do as well if I start with this section. So that is why we're going to begin with techniques of integration. And once everybody has very solid background in integration, of course, we're going to add many new techniques beyond Calculus 1. Then we're going to move on to applications of integration. And applications of integration, in a sense, is where the heart of Calculus 2 is. And I'd like to show you some of the applications that we will be covering in this course. So for example, in Calc 1, without calculus, we can do secant line to a curve, but with calculus, we learn how to do a tangent line or find anything about the rate of change of a function, the slope of a function at a given point. We call this instantaneous rate of change of a function. For example, if it's a distance function, instantaneous rate of change would be your s prime of t, and that would be your velocity, right? So we learned it in Calc 1. We also learned in Calc 1 an application of calculus was finding area under a curve. Without calculus, you can find areas of geometrical known figures. Without calculus, any function f of x, you will be able to find the area under it as long as we can integrate that function. Excuse me. Other examples that we're going to be able to do in this chapter are going to be, for example, finding the arc length of a curve. The arc length of a line, we know how to do from even algebra, but in calculus, basically, we're going from linear structures to nonlinear structures. For example, the surface area of a cylinder we can find by using geometrical formulas, and there are many known geometrical figures that have known formulas. But what if you have something like this, a surface generated by a function? Say you take this function f of x and you rotate it around the x-axis to generate this three-dimensional solid. And the question becomes, what is the surface area of that solid? And other questions we could answer using calculus are questions like, what is the volume of that solid of rotation? So again, we're going to take our knowledge from algebra and geometry one significant level above, and we're going to be able to go from linear ideas to nonlinear ideas. And the basis of all of this, and this is a really underlying principle in all of calculus, is the following. And I'll just give you a little preview right now, but we'll talk a lot more about this when we start the next chapter, which is applications of integration. The idea is, if you don't know how to do something, say how to find the volume of the solid, you take a piece of it. You take, in this case, perhaps just one little cross section of it, which would be something like a disk. A thin disk. If we can find the volume of that thin disk, and we already have formulas from geometry for a cylinder, right? So after all, a disk is a thin cylinder. And then what we're going to do is we're going to separate this given region into n disks, each with a thickness of delta x. And we're going to sum the volumes of these disks. But to find the ideal, the exact volume of that solid, what we need to do is, we don't need n disks, because n disks would have overflows and underflows. It wouldn't cover it exactly, but we need infinitely many disks. So what we're going to do is, ultimately, we're going to take a limit as the number of disks go to infinity, and that sum is going to give us the exact volume of that solid. Now, you may remember doing something like this practice in Calculus 1 when we were finding area under a curve. What we did was we used the idea of using rectangles. We found the area of one rectangle with a base length of delta x. And if you were going from the point A to the point B, we separated that sub-interval into like x sub 0, x sub 1, etc. And so you could find the heights using either the right endpoint or the left endpoint or the midpoint. You know the base, so you know that you can find the area of one rectangle simply by multiplying base times height. And then you add up n of those, and then you take a limit as n goes to infinity. So it's this general idea of solving a problem first. You solve an easier question. In this case, like finding the area of a rectangle is easy, right? And from there, extending it to the original question and then taking a limit to answer the original question. That is really the beauty and just the magnificent thing about calculus, that we can answer very difficult questions by breaking them down into much smaller and easier components and using this magical trick about limits to do infinite sums, basically. So I want to show you one more thing before we start with our review process, and that is, does anybody remember what this quantity represents from Calculus 1? Limit as n goes to infinity of the summation I from 1 to n, f of x sub I times delta x. If you look at just the inner part, summation I from 1 to n, f of x sub I times delta x, maybe that will be a better start. Does anybody remember? That is the sum of n rectangles, because delta x is the base of each rectangle, and f of x sub I is the height of each rectangle. Like, look at the figure over here. The function is given in blue. That's your y equals f of x. And we're going from the point A to the point B. We divided that interval into a partition point such as x sub 0, x sub 1, x sub 2, etc. To find the area under that curve, the first thing you would do would be take the first area, take the first rectangle. The base is what we call delta x, and the height would be, basically, if you're using the right endpoints, take the x sub 1, plug it into the function, and that will give you the height right here. So that would be f of x sub 1. So the area of this first rectangle would be the base, which is delta x, multiplied by the height, which is f of x sub 1. Now add to it the area of the next rectangle. Again, the base is delta x, and the height would be f of x sub 2. Continue in this manner, add n of those, and basically you will have this quantity, f of x sub I times delta x, as I goes from 1 to n. But again, as you can see, we have overflows. In some cases, you may have underflows, especially if you use the left end points in this case. So this is not the exact area. To find an exact area, we need so many rectangles that we're going to have a perfect coverage. In the ideal case, we need infinitely many rectangles. And to accomplish that, we're taking a limit of this quantity as n goes to infinity. And so let me see how many of you guessed the answer correctly in the first place. And the answer was, this quantity represents the integral of f of x dx from a to b. And if for a positive function, like it is in this case, this blue function, it represents the area under that curve. So this was a little bit review from Calc 1 about the meaning of an infinite sum, and about an example using an application of integration. But like I mentioned earlier in this lesson, that we're going to see many more applications of integration, but they will all boil down to the same principle, and that is taking a difficult question, breaking it up into chunks, solving the problem locally in that for this easier problem, and then taking a limit to finish the question and solving the original problem. Now let's go back to our top topics for a moment and take a look at what else we're going to be covering in this class. So we already talked about techniques of integration, and there are several techniques. Of course, the simplest one being U substitution. And we're going to add many other techniques such as partial fractions, trig substitution, trigonometric integrals, integration by parts, etc. Under applications of integration, we've already looked at some topics such as volume, arc length, surface area. Another topic we're going to cover is infinite series. Basically, the first topic is where your test 1 is going to be about. Applications will be your test number 2. It's going to be on that topic. Test number 3, or the third module, will be about infinite series. And there are some very interesting concepts that we're going to talk about in that chapter. Such as adding infinitely many numbers, and does it go to a unique answer? Does it go to infinity? Under which circumstances is the sum of infinitely many numbers a finite answer, and under which circumstances it is not? We can answer some very practical questions as well. In the case of a finite series, we can answer this question: what is the accumulated value of saving, for example, $300 per month for 30 years, say at 6% interest? Um, that would be an example of a geometric series. And we're going to answer, this is perhaps the most interesting thing, and it's the culmination of all the topics covered in that chapter, and that is, can we approximate complicated functions such as e to the x, or ln x, or even trigonometric functions? Can we approximate them in terms of simple polynomials? Because if we can do that, our lives are going to be so much easier in many regards, because e to the x and ln x, they have very complicated integrals, and they're difficult to deal with. They're difficult to find, like ln of, let's say, 1.5, evaluate them. But if we could approximate them as a polynomial, polynomials are very easy to evaluate. Say if I want to evaluate this polynomial at the point 2.1, all I have to do is plug in 2.1 for x. Basically, polynomials are 4 operations, because you have to square it, which means multiplication, add on or subtract. So they're easy to evaluate. So one of the major goals of the third chapter is going to be to get polynomial approximations, and we will see it may not be possible in every instance, but we will see under which situation it is possible, and if so, how can we make use of these twin functions or clone functions in making certain mathematical questions easier to answer, such as integrating difficult functions. Okay, at the moment, we're going to begin with techniques of integration. And the first topic is going to be a review of the techniques of integration that we have learned from Calc 1. And let's take a look at some examples. As a matter of fact, before we look at examples, I would like us to take a look at some formulas that we learn in Calc 1 that are essential and that will be assumed that you know in this class. So let's take a look at those and begin by refreshing your memory about what those formulas are. So let's begin with the integral of 1 over x. Um, Again, I'm hoping everybody remembers these, but it'll be a quick refresher. So this one we've learned in Calc 1 was ln of the absolute value of x plus c. The integral of e to the x. This was the easiest function to differentiate and to integrate, right? Because both the derivative and the integral of e to the x was itself. But what if you have e to the kx, where k is a constant? If you're integrating that, the answer was e to the kx divided by the constant. So for example, if you have the integral of e to the 2x, that would be the e to the 2x divided by 2 plus c. But what if you were differentiating e to the 2x? Does anybody remember what happens then? That becomes 2 times e to the 2x, correct? In differentiation, by the chain rule, you multiply by the derivative of the power, right? It was e to the u times u prime, where in this case u is 2x. Okay, let's recall a few more formulas from Calc 1. The integral of sine x. I think many of you will recall the derivative of sine x is cosine x, but the integral of sine x is negative cosine x. And one way to check, of course, every one of these answers is to differentiate the result. That should give you the initial part. So if you differentiate negative cosine x, you will get sine x. How about the integral of cosine x? Again, we learned in Calc 1 the derivative of cosine is negative sine, right? But the integral of cosine is positive sine. Again, easy to check. Differentiate this side and you will get the other side. Okay, the integral of secant square. Here I'm looking for a function whose derivative is secant square. And that function is the tangent function. Derivative of tangent is secant square. Again, these are important formulas that we need to be very familiar with as we start calculus 2. The integral of tangent function. Now, we didn't really learn something for that, but we learned how to solve this. You can write it as sine x over cosine x because that's what tangent is, right? And then we can do a quick u substitution as I have outlined down here. Let u be cosine x. So its derivative du is negative sine x dx, right? So now I can come back to this integral. On the bottom, since cosine x is u, I'll put a u. On the top, I have a sine x dx to replace, but sine x dx should be the same as negative 1 times du. So I need to integrate 1 over u du, which is actually another, we've already gone over that, the first one, right? That's ln u. Now put the u back, and we get negative ln of cosine x plus c. Just a reminder that at any point, feel free to pause the video to try the problem by yourself first and then continue it to see the solution. That is probably the best way to view these screencasts or videos. Now, sometimes I see the answer to this problem left like this. ln of secant x. Now, how could this be? Any thoughts? Well, if you take this negative sign, remember with logs, if you have like r ln x, you can write it as ln of x to the r, correct? So take that negative, put it up as a power over here. It'll be to the power of negative 1, and of course 1 over cosine is secant, so you would get this answer, but either answer would be perfectly acceptable for me. All right, the next example is integral of sine square. Now, I'm not sure if I covered this in my Calc 1 class, but this is going to come up quite a lot, so I want to make sure everyone knows the following formulas. First of all, that sine square is 1 minus cosine of 2x all over 2. And while we're at it, the cosine square is known as 1 plus cosine 2x all over 2. Now, we have not integrated these yet. We just wrote down what is known as the power reduction formulas. So we need to know that sine square and cosine square can be written as cosine of double angle without the squaring function, and then it becomes easier to integrate them. So for example, in the first one, I can factor out the 1/2. Then I just need to integrate 1 minus cosine of 2x. And integrate 1, you get x. Integrate cosine of 2x. Okay, cosine of 2x, if it had been just cosine x, it would be sine x, right? But in this case, it's going to be sine of 2x. And just like we've seen up there earlier, I guess I forgot to do this one to show you, but just like in case of e to the 2x, if there's an extra constant, you divide by that constant. Like in this case, cosine of 5x, that would be sine of 5x divided by 5, which is easy to check by differentiation, this answer. And coming down here, we're integrating cosine 2x, so that would be sine 2x divided by 2 plus c. Now at this point, I could of course multiply the 1/2 throughout, or you could just leave it like that. Either one would be fine with me. Okay, you can very similarly finish the cosine square one. It's going to be very similar. The only difference is you're going to have a plus sign in the middle there. Basically, that would be the only difference. Okay, what about integral of secant x times tangent x? So now we're looking for a function whose derivative is secant x times tangent x. Do we know of such a function? If you said secant x, you were correct, because the integral of, rather, if we're to check this, secant x plus c. Because if we check this, differentiate this side, the derivative of secant x is secant times tangent. Therefore, that is the correct answer. Okay, let's do a few more integration problems. Let's see. This is another reminder about the inverse trig function formulas. involving integration. So like again, at the end of Calc 1, we had seen these formulas. So just as a reminder, for example, doing this one first, the integral of dx over the square root of 1 minus x squared. Does anybody recall what this one was? This one was sine inverse of x plus c. And how about this one on the bottom? dx over integral of dx over 1 plus x squared. If you said tangent inverse of x, you were correct. Now, if you forgot some of these formulas, again, we're going to need them quite often in this class. And I do want you to know these basic formulas without having to refer to a formula chart on the test. However, to help you remember these formulas, I have prepared a handout about summarizing the formulas I expect you to know coming from Calc 1. And if you go under course-related materials, there's a link called Handouts. Again, that link might be located in different places, different semesters, but if you find a link called Handouts, in there you will see a sheet for formulas, for integration formulas, and it outlines which formulas I expect you to know and which ones you do not have to necessarily memorize. But so far, everything we have seen are formulas that I do expect you to be familiar with. Now, how would we do this one? Instead of 1, if you have a constant a, basically the formula changes a little bit. This one becomes sine inverse of u over a. Again, notice here that u is your variable because u is on the top under du, so that's your variable. So it's very similar to this one, except instead of u, you have an x. In addition, instead of 1, you have an a. And this bottom one is also going to be similar. First of all, you see the sum of squares on the bottom. You should remember this is tangent inverse function. Tangent inverse of u over a. And we also learned that there was an additional 1 over a in the formula for the tangent function. Again, these are formulas I do expect you to be familiar with, and they should be listed on that handouts list. All right, so these were basically not review of techniques of integration so far, but just a review of formulas. But the main technique of integration you learned in Calc 1 was U substitution. So I want to take some time to go over plenty of questions using U substitution. The main reason for that is every other technique that we're going to learn in this chapter, in Calculus 2, will rely on U substitution. So that's a very important technique, and you need to be very proficient at it before you move on with the other techniques. Let's see, some more examples. Okay, so before we do U sub, let's do an example where we don't need U sub, and all the other examples I think I'm going to have will include U sub examples. Okay, let's start with this one. So you have a sum of 4 quantities, and we know that the integral of a sum is the sum of the integrals. So you can integrate one at a time. Of course, we don't have such a rule for multiplication or division, but let's just go one piece at a time. The integral of e to the 2x, for instance. That would be e to the 2x divided by 2. The integral of x squared, we learned the simple rule x to the n plus 1 over n plus 1, right? So that's x to the 3 over 3. Now, 1 over root x, I'm going to begin writing it without a square root. So this is the same as x to the power of negative 1/2. Now, once again, applying the power rule, so add 1 and divide by the new power. So you will have x to the 1/2 divided by 1/2. And the last item, the integral of sine of 5x, that will be negative cosine of 5x divided by 5 plus c. So the only way that I might simplify this again is just rewrite it, the middle term, get rid of that fraction on the bottom, on the third term. So we have e to the 2x over 2 plus x cubed over 3 plus 2 times x to the 1/2. You could say 2 times the square root of x there, minus cosine of 5x over 5 plus c. Okay, let's take a look at the next example on integrating it. This time we're going to need u substitution because again, we cannot do the integral of the top over the bottom. There is no such rule. That's pretty much what makes integration difficult. Like in differentiation, you have a product rule, you have a quotient rule. In integration, we do not have that luxury. So we have instead u substitution and many other techniques to try to get around that problem. So in this case, I'm going to use u substitution. What would you select u to be? Not that many choices here, right? If you let u be x squared plus 25, as you recall, you want the derivative of u to be in this integrand to begin with up to a constant. In other words, you don't worry about the constants. You can always factor this 3 out. But what is the derivative of u in this case? It is 2x dx. And we already have an x dx up there, so we know this is a good sign. We know this problem will work with u substitution. Now, I know different students or different instructors do this differently. This is the way I taught in Calc 1, so I'm going to continue in the same way. But I know that there are ways to look at this problem and immediately, write down the answer, at least for a simple u substitution like this. But in general, I really want you to show your work as much as possible. But if you can do it in your head quickly with that other method, you can always check your answer that way. So in this case, I take the 3 out. I'm going to write the integral in terms of the u's now. Instead of x dx, x dx is going to be the same as du over 2. I'm putting du inside and over 2 outside. And x squared plus 25 is what we call u. Now this looks familiar, right? This is the integral of ln of u plus c. And don't forget to put the u back in there when you're done. So u is x squared plus 25. Again, we can easily check this by differentiating the answer and showing that we will actually get the given example. So let's just do that real quickly. Like the derivative of ln u is 1 over u times u prime. In this case, we don't even need absolute values because x squared plus 25 is always positive. So if you differentiate that, you get 1 over u. So here's the checking process. 1 over u times u prime, which is 2x. This is the derivative of ln x squared plus 25. But you had a constant up front. That constant remains as it is when you're differentiating. If you have c times f of x, the derivative will be c times f prime of x. If all you have as a constant, the derivative is 0, right? But c times f of x, the constant remains, you differentiate the function. And now if you simplify, the 2's cancel. So you end up with 3x divided by x squared plus 25, which of course is the answer, the given expression that we started with. So we know this is the correct answer. Now sometimes checking can be very time consuming, so I'm not suggesting that you check every time. But from time to time, it cannot hurt. It's also good practice on differentiation when you check your answers. How about the very next example you see on the screen? This one. How would you go about this one? It's so similar to the last example, but can we use u substitution here? Think about it. Okay, so if you let u be x squared plus 25, you're going to have x dx to deal with, but there is no x on the top, right? So in this case, we cannot use u substitution. So let's think about it. Are there any formulas that we have learned that would apply here? Well, flip back a few pages from today's notes, you will see that you were reminded of the arctangent formula, right? When you have the sum of two squares on the bottom, this is x squared plus 5 squared on the bottom. So what is your a? A would be 5. So the formula, take the 3 out first of all. So 3 times, the formula says 1 over a times tangent inverse of x over a. In this case, our a is 5, plus c. So of course you could leave this as 3 over 5 times tangent inverse of x over 5. So just notice a slight change in the problem, but a completely different way in which we solve that problem. So look at it very carefully when a problem is given to you and decide whether U substitution applies or not. For example, this next problem, could I use U substitution here, or could I use one of those inverse trig functions once again? Well, because we have that cube root sign on the bottom around x squared plus 25, there is no inverse trig function formulas when you have a cube root sign. Now, if we had the square root and difference of two squares, it has to be like exactly like the formula we have seen. If you had something like this on the bottom, 25 minus x squared, yes, that one can be done with inverse sign, but not this one. Let's think about, can we use U substitution? Here's a trial. If you let U be x squared plus 25, its derivative is 2x dx. And once again, there is an x dx on the top, so this one will work with U sub, right? So let's rewrite everything as a U sub. So the 3 can be taken out. Instead of x dx, once again, I'm going to have du over 2. For the bottom, this is the cube root of u. Rewriting this, and applying the exponent rule for integration, we get this. So just add 1 to the power, or 3 over 3, so you get u to the 2/3. Divide by 2/3, which is the same as multiplying by 3/2. So I'm getting 9 over 4 times u to the 2/3, and I'm putting the u back in here as well, to the 2/3 plus c. So that is the antiderivative for the given function. And sometimes you can also have, of course, limits of integration. Like I do an example here for you. Say you have the same exact problem, but it has the added limits going from the square root of 2 to the square root of 39. So basically, once you find the antiderivative, you would put your limits as, again, you're going from a to b. And of course, we always plug in the upper limit first minus the lower limit, right, by the fundamental theorem. If you like, at this point, take a moment to finish the problem and then come back and check your answer. So we're going to plug in root 39 first for x, and then root 2 next. So we go f of b minus f of a. So if we do that, we're getting 9/4 can be taken outside, so 64 to the 2/3 minus 27 to the 2/3. And you can use a calculator, but in this case, 2/3 means the third root and the second power. So first take the third root. Third root of 64 is 4, and the square is 16. And 27, the third root is 3 to the second power is 9. And here we have 16 minus 9 is 7. So our final answer is 63/4. Okay, we're going to continue the rest of the examples in this part 2 of this recording.